and see what fit. So let me open the file first. Last week we were at I think homework was the last two questions of permutation and combination. Okay, so let's look at the question here. So for the last question on question 12 and question 13. So let's look at the first one, part 1. Okay, so for the first question, for the rectangular shape, which we put A, B, C, D, E, F, G, H, I, J. Okay, there are different, we can put the canisters on it. So we look at here, find the number of ways in which the canisters can be placed if two particular canisters must not be placed on any of the base A, E, F, J as they are next to the door. So we can actually cross, for the first part, we can cross A, E, F, J out. So for the remaining 6 places, the two canisters can choose 2 places to place it. And then within themselves can permutate. And the remaining 8 can anyhow permutate. There's no restriction at all. That's the working for the first part. So we do 6 choose 2 to place the 2 canister, okay, the 2 particular canister. After that, the 2 can, within themselves, can permutate. Then times 8 factorial, the remaining 8 can actually permutate again. So this is the answer. And for part 2, 2 of them cannot be next to each other. Okay, we can do in a way such that method of complementation, we find the total number of ways. We can find the total number of ways, which is 10 factorial. Then minus 8 choose 1, which is to put the 2 particular canisters together. Okay. So why do we do 8 choose 1? Because there are only 8 possible cases that we can do that. So let me see, let me show you, like, could be like this, while the position or here. Okay. So basically there are 8 possible ways to put the 2 canisters together. So we find the number of ways that the 2 canisters are together. Okay. After that, we'll let the 2 canisters to permutate between themselves. So times 2 factorial, then times 8 factorial for the remaining canisters to permutate. Yeah, this is how we do it. Any question? It's not an easy question. Okay, I'll give you 1 minute to process. After that, we do question 13. So now let's continue. Go for the effort. So for question 13, when we want to put the 12 people, okay, without restriction to arrange them, it is something like to put the 12 people into 3 groups. Each group will be with 4 persons. Okay, so how many ways are there? So we'll be doing 12 factorial divided by 3. Okay, because the ABC side, we call them ABC side, actually are the same. So we should divide it by 3 to avoid the double counting. So let me show you the working on the small drawing board. We have 12 factorial divided by 3. Get this. Yeah. And then part B, part 2, find a number of different possible arrangements if each man sits next to his wife with both husband and wife on the same side of the table. Yeah. So basically we can do 6 factorial. Okay, because we'll put the 12 people into 6 groups, which each group is of a couple, a married couple. So that's 6 units. And then divided by 3 because there are 3 sides, right? And then after that, we'll let the couple within themselves to permutate. So it's 2 factorial to the power of 6. 2 factorial to the power of 6. Okay, so far? So we have 12 factorial divided by 3 to get the number of combinations when there's no restriction. And then we want the husband and wife sit together as together. So basically we can do 6 groups of units, 6 units factorial, then divided by 3 times 2 factorial to the power of 6. 2 factorial means husband and wife and husband can internally permutate. It could be husband and wife, be wife and husband, so it can internally permutate. So it will happen for 6 times. Yeah, that's all. Anything else you want to ask? If no, we'll look at probability. So we'll be starting probability as a new topic today. Yeah, so we look at the introduction. An experiment is a situation involving chance or probability. Okay, so for example, we are going to roll it. For example, the example is like rolling a die. Okay, and then an outcome is a result of an experiment. So the possible outcomes are 1, 2, 3, 4, 5, 6 for us to do the experiment, which is rolling a die. And then the sample space S is the set of all possible outcomes. Could be 1, 2, 3, 4, 5, 6. This is the sample space. Because we talk about a set, So the elements in the set are 1, 2, 3, 4, 5, 6. These are the elements in the set. And then an event A is a subset of the sample space. Okay, for example, we take the even number, okay, we can have 2, 4, 6. Okay, so do take note that there are some very basic concepts on probability. The probability must be within 1 and 0, cannot be less than 0, cannot be 1, 1. Yeah, and then the complement of A, we can have, like, for example, we have A equals to, let's say A equals to 1, and complement of A equals to 2, 3, 4, 5, 6. So I believe you still remember a little bit on the Venn diagram, which you learn in secondary school. So if you have, I don't show so many circles. I give you a simplified version of Venn diagram. So for example, inside is A is the inside. So what about A complement? Is whatever not there inside the A. Okay, so far? So now we look at example 1. Okay, so in the casino game of roulette, the table and the wheel are laid out as what we can see here. Okay, so find the probability that the player wins if the place on a single bet is marked as 7. So how do we do this? We need to find the total number of possible outcome. What is the total number of possible outcome in this case? What is the total number of outcome in this case? In this case, what do you think? Total number of possible outcomes in this case. We can actually see that altogether 37 possibilities from 0 to 36, 37, right? That's a total. So to get a number 7, which is only one out of the 37 combination, the probability is 1 out of 37. And then for next part, the pocket marked red, for the cases that the pocket is marked red, you can see from the diagram here, it's either red or blue. One of them is green. So we have 18 out of 37. Then for the second dose, you can see it's basically inside this particular box. How many numbers are labeled with the second dose? 1, 2, 3 times 4, which is 12. So we'll get 12 out of 37. Look at the explanation here. There are 37 outcomes. All of them are equally likely to occur. So to get the 7, that's basically only 1 out of 37. 1 out of 37. Second part is we look at the roulette. Basically, we have only one green. The rest are either blue or red. So we have 18 out of 37. Yeah. So there are 12 numbers. So for the last part, there are 12 numbers from 13 to 24. So we can get 12 out of 37 for the second dozen. Okay, so far. Now let's look at example 2, because both of you have learned probability in school, I suppose. Santosh have started already, right?
Okay.
Okay, yeah. So I wanted to try question 2 by yourself, and then you type out the answer. I'll show you the partial working is actually on the board. Strategies, for example, construct a table, and all that is already in the notes. So I want you to give me the final answer for question 2. You can type it out. Santosh, your part 3 not exactly correct. Santosh, I put the answer on your board for part 3. So you can actually list down the combination. These are the possible combination for part 3. It is either 2, 6, or 3, 5, or 4, 4, or 5, 3, or 6, 2. So each one is 1 out of 36. Then we have 5 such combination. Therefore, it's 5 out of 36. Can you understand, Santosh? Stand now, Santosh. Okay. So now we look at 4 and 5, Santosh. Tamika, your part 4 is good, but not the last part. Class, I gave you 1 more minute to try the question. Okay, so let me show you the working for the last part 4 as well. Yeah, part 4 and the last part are similar. We can use the construction of a table to solve. So let's look at the table for part 4 first. So we look at the sum. Okay, these are the sum. The sum of the numbers on the 2 dice exceeds 8. We see the gray color part. How many are there? 10. So 10 out of 36 equals to 5 out of 18. That's it done. Okay, so far. Then we look at part 5. Okay, so for part 5, we will look at the differences. So there are different value for the difference. Could be from 0 ranging all the way to 5. So we put the two corner which are of difference more than 2. More than 2, it means greater than 2. 2 is not included. More than 2, we can interpret it as more than 2. So we look at the ones 3, 4, 3, 4, 5, 3, 3, 4, 5, 3, 4, 3. Okay, so the final answer is 1/3. Okay, so far. So now we look at the part of the question. So can I give you some time to read question 3 first? I'll give you 1 minute to read question 3. We look at the explanation. So we use this method called method of complementation. Okay, so we can do probability of winning the first game, okay, is 1 minus there's no p. So what's the probability of no p? 5 out of 6, 10 to the power 4. That's how we get the probability. And for the second game, instead of finding the probability of getting 12 or a double 6 in 24 rows of 2 dice, Pascal found the probability his friend losing not rolling a double 6. Okay, so for not having a double 6 is 35 out of 36. Not a double 6, it's 35 out of 36. And it happened for 24 times. No double at all, right? It's 0.509. So the answer is 0.491. So this is called method of complementation. We use 1 to minus the probability that the given condition is not satisfied. Then we get the probability the given condition is satisfied. Yeah. Okay. So now we look at our Venn diagram. Just now I drew a simple Venn diagram. So A complement is outside. Whole thing is called the sample space. This S represents the sample space. Yeah, okay, so far. So we have A union B, probability of A intercept complement of B. Then we have probability of A complement intercept B complement. Okay. So let's look at question 4. So we can draw the diagram. So for A and B together, it is 0.5. So A itself is 0.3. B itself is 0.4. So which means if we want to find A intercept B, we're looking for this part, which is 0.3 and the 0.4. We can add them up, subtract 0.5. Then there's a part which is double counted. Because here we added twice, the intersection part we added twice, so we get 0.2. Then we will shade the region of A union B complement. So basically it's in A, but not in B, which is this part. This is the probability of A intercept B complement, which is the entire A minus the part not in A, 0.5 minus 0.2. Okay, so the next part, A complement union B. Like this, it is 1 minus 0.3, which is 0.7. That's all done. Okay, now we look at the next part, which is mutually exclusive. Okay, so mutually exclusive means there's no common element. A intercept B is a null set. This symbol is a null set, means no element. We can also use the set notation with no element inside to represent the null set. Okay, so far. So mutually exclusive means intercept is 0. So there's nothing double counted if you use probability of A plus probability of B to get probability of A union. Okay, so there's another concept called conditional probability. Conditional probability is basically the probability of A given B. So it's given, this part is called given B. That means when B is definitely happening, what's the probability of A? So the formula is here. Okay. Probability is A given B equals the probability of A intercept B divided by probability of B. Okay, so far. So now let's look at example 5. 2 ordinary dice are thrown. Find the probability that the sum of the number on the 2 dice is 4. Given, this is the given condition, given that the number on the 2 dice are equal. So you can see the working here. We use the formula A given B is probability of A intercept B divided by probability of B. The numbers are equal. You have 1, 2, 3, 4, 5, 6. 6 combination. So out of the 6, there's only one possible case, which is 4 and 4. So it's 1 out of 6. Sorry, this is more of the second method. The first method is the probability of getting a 4, 1 out of 6. Getting a 4, 1 out of 6. divided by 1 over 6 times 1 over 6 times 6. So we can cancel, we get 1 over 6. This is for question 5, part 1. Now we look at part 2. The number on the two dice are equal, given the sum of the two dice is 8. So we can do the listing down method. So you can see this right hand side is my preferred method. I have a 1 here, divided by out of 1, 2, 3, 4, 5. I can also do 1 out of 6 times 1 out of 6 divided by 1 out of 6 times 1 out of 6 times 5. So the answer is also 1 out of 5. We have independent event. I think Pamika doesn't need to know this. Pamika, you haven't seen this before, right? Independent event.
I remember learning it.
Oh, you remember learning? Okay, yeah. So for independent event, is basically possible cases are, so basically probability of A given B is still probability of A. So basically they are not related. Yeah. So no matter B happen or not happen, A still happen in the same way. There's no difference. So to show the two events are independent, we can have this possible case, this possible case, this possible case. These are the three formula. We can interpret it as when the two events are independent, okay, A and the B complement is independent. A complement and B are independent. Complement of A and the complement of B are also independent. Okay, yeah. So let's look at example. I want you to try to do example 6 by yourself. Okay, I'll show you the notes here, how you show two events are independent, and I'll put the question on the left hand side. You can do the working on the board on the right. Start trying now. This is slightly harder than the question just now. Do you need help? Oh yes or no?
I'm not sure how to do part 2 or
Okay.
ENP.
Santosh, okay so far? Shall I explain to you or no need?
I'm still trying.
We're still trying. Okay, so I explain to Pamika first. So Pamika, for example 6, part 2, you want to find whether they are independent. So what you can do is find the probability of A. Okay, so drawing an ace is 4 out of 52, which is 1 over 13. That's part 2. And then probability of A given B. So given this is a spade and it's an ace, is it 1 out of 52? There's only one such card. Agree with me? So probability of this is probability of A given B. It's still 1 out of 13. Basically, no matter B is a spade or not spade, it still only have like no difference. Like A still have 1 out of 13 chance. So probability of A given B equals the probability of A. Therefore, they are independent. A and the B are, which is here. The first one, the first result. Okay, so far.
Sorry, can you explain again why probability of A given B is 1 over 13?
Oh, because no matter what the B is, okay, it doesn't really matter whether the card is a spade or not spade. The probability of having an A still as 1 out of 13. You still have only 4 cards which are ace out of the 52 cards.
Okay, thank you.
Okay, I'll give you another 3 minutes to try. You can type out your answer already. Okay, like yes or no, can already. Yeah, sometimes you can just write down yes or no. Just write yes or no. No need to write so much. Are they? Oh, just yes or no. Santosh, have you done part 3 and part 4? Or still do? Oh, you're still doing. Hi, Santosh, are you still doing question part 3 and part 4? Pamika, is this answer for part 2? Then okay. Then you are doing part 4, right, Pamika? Pamika may double check your final answer for part 4. Okay, Santosh, good job. If you have done the 4 parts, you can take a break now. You can take a break after the 4 parts. Pamika can take a look of last part again. Okay, so I go for a toilet break. After that, we can discuss. Pamika, do you understand the last question? Do you want me to go through?
I understand the last question.
Okay, great. Thank you. So we look at this is a very, very important part called probability tree. Hi, Santosh, are you back? Can you turn on your camera? Thank you. Okay, probability tree is very important. Actually, we learned this in secondary school, just that in JC, we'll learn something a bit more interesting, a bit more challenging as well. Okay, so a probability tree, which is also known as a tree diagram, is a useful way of considering the outcomes of a series of experiments. Okay, so let's look at example 7. In an experiment involving the toss of biased coins, the probability of obtaining a head is 1/3. Second coin is sorry, first coin and second coin is first and second coin is 1/3 and 1/4, 1/3 and 1/4 respectively. Okay, so the first coin is tossed, and if it shows a head, then the first coin is tossed again. If the first coin tossed is not a head, which is a tail, then it will have the second coin tossed instead. Okay, so you can see the first one, A representing a head for the first one. So the probability not showing a head is 2/3. Okay, so after the first one being tossed, if it's a head, then continue toss the head. So we'll get 1/3 again for the probability of having a head. Okay, so the first outcome is head and head. Then this would be 2/3, which is head and tail. We can have tail and then head and then tail and the tail. So let's look at the first one. Probability of B complement. B complement could be this case and this case, given that A. Yeah. So we will just look at the probability of one of the branches, which is just this probability of B. Okay, just look at here. We don't look at anything else. We look at where my cursor is pointing at. We're looking for the probability of a B complement given A. So it has to go this branch followed by that. So the probability is 2/3. Then the probability of B could be probability of AB plus the probability of A complement B, so that we can find the final answer, 5 out of 18. Okay, so far, I'll give you 30 seconds to process the information here, then we can move on to the next part. Now let's look at the next example. The probability tree is partially filled in. Okay, you use this to do question 8. There are 3 parts, 1, 2, 3. Okay, I want you to look at the question and try this question now. Let's spend 3 minutes on it. Santosh, good job for part 1. Tamika, good job as well. I think we need more time. I'll give you another 4 minutes to try the best. Santosh, is the denominator 5 or 3 for part 2? Sorry, I still cannot see. You type out the words. Oh, okay. Not really correct. No, not really correct. Can I go through part 2 with you? Part 3, you can try it by yourself later. So first of all, we may need to complete the probability tree diagram. So we have 2 red ball and 3 green ball. So after we have red and green, how many green are there? 3 balls out of 2 of them are green. So red is 3 balls out of 1 of them is the red. Okay. Then if it's red and the red, then for sure it's 1 that's going to have the green, because the both red balls are drawn. Okay, so let's look at the flow one more time. Start from the first draw. When we draw a ball, we have 3 fixed chance to get a green, 2 fixed chance to get a red, and then second ball could be a green, could be a red, half chance. Then because I have 2 green gone, I only have 1 more green left. So out of 3, so then 2/3. Then green, red, green, green, red, red. Okay, red, green, green, red, green, red, and red, red, green. And then we look at part 2. Exactly 1 red ball is drawn, given that the first ball drawn is green. So we only look at here. So we can take the chance of green, green, red, and green, red, green. These are the 2 cases. So the first ball we do not need to consider. So it's these 2 and these 2. That's all. Okay, so basically we take it the first ball is already drawn, which is a green. Then we start the calculation from here. Starting from here, green, red. Start from here, red, green. Then find the sum. That's all done. Okay? Can you understand? So we do not need to consider the 3/5. I suppose some of you, some of you have 2 out of 5 as an answer, because you still consider the first event, which is 3 out of 5. But 3 out of 5, no need to consider already. It's only look at, since the first one is green, what is going to happen next? Okay, let me repeat. What is going to happen next? So now please try part 3. Okay, please try the next part now. Part 3. And then also got part 4 lah. Are the events exactly one of the balls drawn is red and the first ball drawn is green independent? This one is not yet. It's like a part 4, kind of part 4 of the question. It's an independent part. It's like a separate part, I shall say. Independent sounds very misleading. Yeah, let me check your answer. Once you get answer for 3 and 4, please type it out. Santosh, your answer not exactly correct. Not really. Santosh, closer, but still not correct. Okay, let me show you the answer. Okay, this is working. Basically, the part 3, the first ball is green, given that exactly one red ball is drawn. It could be green. You need to get this first. So if the first ball is drawn is green and exactly one red ball is drawn, divided by the probability that exactly one red ball is drawn. Okay, exactly one red ball is drawn is the answer from the previous part. Our answer from part 1. So we find the probability of green, red, green. Okay, this is green, red, green. And then green, green, red. Then we divide that by 3/5. And we get the answer as 2/3. Okay, so far? Yeah, okay. So for the last part, you are supposed to find whether the two events are independent. The working is here. So since the probability of exactly one red ball is drawn, given the first ball drawn is green, is not equal to the probability of exactly one red ball is drawn. The two events are not independent. They are not independent. Okay, we have covered all the concepts already. Just let you know that certain question, besides using probability concept, we also have to use P and C. That's why we learn P and C first, followed by probability. That is the reason. Okay, so let's look at example 9. It is known that in a large population, 10% of the population has blood group AB. 3 people are randomly chosen, one at a time from the population. Okay, find the probability that the first person has blood group AB and the second one do not. A second and third one do not. How do we do this? Because it's a large population, so we'll do the first one, 10%, doesn't affect the second person and third person. So we can get the answer as 0.081. So question 9 is similar to exam question already. Previously, the questions are still considered relatively easier. So from here onwards, the questions are getting harder. So now we look at part 2. Find exactly one person have the blood type AB. What we do is we will use this 0.081 to times 3 factorial divided by 2 factorial, because we can actually permutate. It could be AB not A, AB not AB not AB, could be not AB AB not AB, could be not AB not AB AB. So there are different permutation you should consider, different order that you can consider. So we use the 0.081 times 3 factorial divided by 2 factorial. So this part is to consider the number of ways can be arranged. Okay, so we get the answer as 0.243. Now we look at the last part of the question. Okay, look at the last part of the question. At least one person has blood group AB. Okay, we can use the method of complementation. We use 1 minus none. Now means the first one is non-AB, second one non-AB, third one non-AB. So we can get the final answer as 0.271. Okay, so these are the parts that for question 9. Any questions so far? If no, I'll move on to the next part. No. Okay. So now let's look at example 10. Okay, I want you to try example 10. If there's any part you are not sure, we can discuss together. I think I can give you 5 minutes to try it out. So you can type out your answer now. Okay. Both of you didn't get the first part correct. Santosh, your second part is okay. Good job. I understand Santosh's mistake, but I think Pamika's one, Pamika's second part is also correct. Thank you. For the first part, let's discuss. The probability of having a number card is 40 out of 52. The probability of having the picture card is 12 out of 52. So the probability is number card plus picture card, or picture card plus number card. There are two possible cases. Okay, then we can simplify from here. You need to consider number. You see a number card followed by picture card. So you see it's like after the number card, we get the picture card. So we do multiplication here, right? Then or is we do addition. Then multiplication again. You see, we have number card followed by, and then after that, we choose a picture card, 11 out of 51. So one after another, there's a sequential concept. Okay, there's a sequential concept here. Okay, and then then this event and this event, they are mutually exclusive. Okay, so then part 2, both of you did very well. Then we look at part 3 now. Part 2, both of you did very well. Do you understand part 1 now? Part 1, okay? I hand out the drawing board now so that you can type out your answer. Okay, I'll go through with you now. I don't see the correct answer. We want to do this approach, which is listing down possible combination. In order to have the sum as 18, you have 8, 10, 9, 9, and 10, 8. So first case is 4 out of 52 times 4 out of 51. Remaining 51 cards, but 4 of them are 10, right? So you have 8 and then 10. Then the second case, out of the 52 cards, 4 of them are 9 times 3. Out of the 51 cards, 3 of them are 9. Okay? Then you plus 4 out of 52 times 4 out of 51. Then final answer is 11 over 663. Okay so far? Okay so far, everyone? Can?
Like
First
the
one is number.
sequence.
If you consider, you see, if you consider the order, you may want to do, you can consider the order like 8 and 10 as a combination. So it's 4 out of 52 times 4 out of 51, then times 2 factorial. This is okay. But for number 9 and number 9, you do 4 out of 52 times 3 out of 51. Then you times 2 factorial. But 2 of them are the same, so you divide it by 2 factorial. They cancel. They cancel, right?
Okay, thank you.
Okay, yeah. So let's do the next question. Santosh, can I understand my working for part 3?
And I do like 3 over 100 times 40 over 52 times 39.
Sorry, 3 over 100.
Yeah,
Where does the 100 come from?
it's like the sum of all the numbers. Like I drew a table out.
Can you upload your table? I hand out the drawing board. You take photo and upload your table. Then I can figure out which part went wrong. Pamika can do question 11 now. Santosh, type out your you take photo and upload your table. Let me take a look. I don't think it is correct because there are first of all, there are other cards which you didn't consider, not only the number cards. Secondly, if you do 1 to 10, 1 to 10, they are not affecting each other. They have all the, like 1 is equals to 2. But then you have to consider the probability here, right? Like it's correct to say 18, 18, 18. So you have to consider 10 and 8. Like what is the probability of having a 10? What's the probability of getting an 8?
Just like what I did was like I considered like the possibility of getting 18 out of like all these combinations. Then I multiplied by the probability of getting 2 cards, like 2 number cards.
Okay, so you get this out of 100. Then you times the probability of getting 2 number cards, which is 40 over 52 times 39 over 51. Is it like this?
Yeah, that was what I did. But like, I don't understand why that's wrong. Like why this method would be wrong.
Let me try to explain to you. Okay, from your table is as if 8, 10, 10, 8, and the 9, 9 have the same probability of getting it, which is incorrect because 4 and the 8, 8 and the 10, and the 10 and the 8 is easier because you got 4, 8, and the 4, 10, and if 10, 8, there is also 4 and the 4. But you look at 9, 9. At first you got 4, second one you only have 3 such cards. So if you use this particular method, it's as if this set 1 to 10 number cards and another set of cards 1 to 10, rather than we put all the cards together in one set.
Okay.
So your method is more of you have 2 boxes. Box A 1 to 10, box B 1 to 10. Then you draw whatever number from A is not going to have any impact on in the B's the number you draw from B. They are independent, which is not true in this case because your first card, if it's a 9, the second card is a 9, it's only got 3 more. 8 and 10 you can use. If you just do a question of 8 and 10, maybe still okay because 8 and 10 are kind of independent, it doesn't affect. But the 9 and the 9 is from the same set of paper, which is not appropriate. Your method is more of something like this. Yeah. Okay, thank you. I noticed it's the end of the lesson already. Can you try question 11 and 12 as homework? These 2 questions are tough questions. Question 11, question 12. We'll go through next week, and next week we'll start the next topic, binomial expansion. Santosh, do you have any upcoming test?
I have term assessment next week.
Next week, is it?
Yeah.
What are the topics tested?
Integration
Integration, okay.
and
PNC.
PNC and probability
Okay.
and Maclaurin's expansion.
Okay, so it's good that we cover probability today. Yeah, so do you need any practice paper?
Don't need, I already have a slew.
Okay, can. Then we will just continue probability, and by next week, we will do binomial expansion. Yeah. Pamika, your test is not so soon, not next week. I remember your parents sent me the date.
I just had assessment today, term assessment today.
Okay,
Like,
yeah. How was it?
It was there was a question with like unknown normal distribution. That part I didn't know how to do, but the rest was still okay. Like unknown mean and unknown variance, then they ask for like W1 minus 2 of standard deviation is less than W2. But I didn't know how to calculate because the mean and variance are both unknown.
Okay, can you send me the question if you have? Yeah.
Okay, I will try to type it out.
Okay, perfect. You can text me. Okay, thank you. Yeah, thank you. So that's all for the lesson today. Homework is 11:12. We will start new topic next week. Thank you, everyone. See you next week. Bye-bye. Thank you.
Thank you. Bye.
Bye-bye.
Thank you.
Bye.